Space does not feel fragile. It feels vast, continuous, endlessly present. Yet, physics tells us something quietly unsettling, that space itself may have a limit, a smallest possible scale where the idea of distance dissolves and the universe stops behaving like a place at all. At around 1/10,000,000th of a billionth of a billionth of a billionth of a meter, our best equations stop agreeing. Gravity and quantum mechanics begin to contradict each other. Space no longer stretches smoothly. It flickers. It fractures. It may even stop existing in any meaningful sense. If this quiet journey into the deepest edges of reality brings you even a moment of calm or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep this calm corner of the universe alive, and I hold that support with sincere thanks. Now, we turn the page and begin with the first truth. Part 1. How small can distance really be? If you could keep zooming in forever, past skin, past cells, past atoms, would the universe continue revealing smaller layers without end? For centuries, physics assumed it would. That space was smooth, divisible, infinitely zoomable. But modern experiments suggest something else entirely. A boundary where the idea of closer quietly breaks down. At first, the journey inward feels familiar. You pass the scale of everyday life without effort. Skin gives way to cells, cells to the delicate machinery inside them. Molecules drift apart like loose constellations. Atoms appear mostly empty, tiny nuclei surrounded by vast regions of probability where electrons hum rather than orbit. Already, the universe feels less solid than it once did. Keep going. Beyond atoms, you arrive at the nucleus, a region so dense that nearly all of an atom's mass is packed into a space thousands of times smaller than the atom itself. Protons and neutrons cluster tightly together, bound by forces that do not exist at larger scales. This was once thought to be the end of the journey, the indivisible core of matter. But it wasn't. Experiments in the 20th century revealed that protons and neutrons are not solid objects at all. They are made of even smaller components, quarks, held together by gluons in a restless, energetic dance. At this scale, nothing sits still. Particles appear and vanish. Energy flows continuously. Matter behaves less like tiny balls and more like vibrating relationships. For a long time, this seemed reassuring. Every time physics reached a boundary, it found a deeper layer waiting beyond it. The universe appeared generous with its secrets. Smaller distances simply required better tools, higher energies, more patience. That belief shaped an entire worldview. Space, in this classical picture, was like an endless sheet of fabric. You could cut it in half, then in half again, and again, without ever reaching a final thread. Distance had no minimum size. You could always go closer, always divide. Further, always zoom in one more step. But nature, it turns out, may not agree. To see smaller things, physics relies on waves. Light is the most familiar example. Its wavelength sets the limit of what it can resolve. You cannot use long, gentle waves to detect tiny details. To see something smaller, you need shorter wavelengths, which means higher energy. This rule is not a limitation of technology. It is a law of nature. As scientists built more powerful microscopes and particle accelerators, they followed this rule faithfully. Each new generation used more energy to probe smaller distances. And for a while, the universe responded as expected, revealing new layers of structure with quiet consistency. But then something subtle began to happen. As the energies involved grew extreme, the act of looking closer started to interfere with the very thing being observed. Concentrating enormous energy into an incredibly small region began to bend space itself. This was no longer a problem of measurement, it was a problem of reality reacting. According to the physics of gravity, energy and mass are interchangeable. Pack enough energy into a tiny space and space-time curves. Increase it further, and that curvature becomes so strong that not even light can escape. In other words, beyond a certain point, trying to see smaller distances would create a horizon, a boundary beyond which observation becomes impossible. This realization marks a profound shift. It suggests that the universe enforces a smallest meaningful scale, not because we lack cleverness, but because space itself resists being divided indefinitely. The closer you try to look, the more violently the geometry of space responds, until the concept of inside loses its meaning altogether. This is where the idea of a fundamental limit emerges, not as a technological obstacle, but as a structural feature of reality. At this limit, the very language we use begins to fail. Distance assumes there are 2 points separated by space. But what if space is no longer smooth? What if it flickers, fluctuates, or dissolves into something more abstract? In such a realm, asking how far may be as meaningless as asking for the edge of a thought. What's especially unsettling is how quiet this boundary is. There is no explosion, no warning sign, just a gentle breakdown of our assumptions. The equations stop agreeing. The predictions lose clarity. Space itself becomes uncertain. This challenges one of the deepest intuitions humans have ever held, that the universe is built from smaller and smaller pieces, like an infinite set of nesting boxes. Instead, reality may be layered only up to a point, after which it changes character entirely. Even more strangely, this limit is not imposed by any particular material or force. It appears to be universal. Whether you are examining empty space, dense matter, or the heart of a star, the same boundary applies. Space itself refuses to be examined beyond a détente. Certain resolution. From a human perspective, this feels almost intimate. We live our lives surrounded by distances, between places, between moments, between people. We measure progress in steps and years. We imagine infinity as something vast and far away. Yet here, at the smallest scales, infinity quietly disappears. There is something calming about that. It suggests the universe is not endlessly fragmented, not infinitely sharp. It has texture, limits, perhaps even a kind of softness at its foundation. Beneath all complexity, there may be a smallest grain beyond which division simply does not apply. And yet, this smallest scale is not something we can picture. It is far beyond imagination. Numbers lose their meaning there. Comparisons fail. To say it is small does not do it justice. It exists more as a boundary condition than as a place. You cannot stand there. You cannot point to it. You can only approach it in equations, watching familiar concepts slowly dissolve. As you rest here now, breathing steadily, it's worth noticing how different this is from everyday experience. The room around you feels continuous, solid, reliable. But beneath that calm surface lies a universe that may not be continuous at all, one that hums with limits and thresholds hidden far below perception. Physics, at its deepest level, is not about certainty. It is about humility. Each time we ask how far something goes, the universe answers, gently, precisely, and then asks us to reconsider the question itself. So how small can distance really be? We don't yet know in the way we know the length of a table or the width of a room. But we do know this. There comes a point where space stops behaving like space, where closeness is no longer defined, where the universe no longer offers smaller layers, but instead offers silence. And as we continue this quiet journey inward, one question naturally remains. If distance itself has a limit, what exactly happens at that final edge where space can no longer exist? Part 2. The Planck length, nature's smallest ruler. There exists a number so small it barely feels real, about 1.66 1035 meters. This is the Planck length, not because we've measured something that small, but because below it, the equations of reality lose their meaning. At this scale, distance itself may no longer exist. To understand why this number matters, we need to pause and consider what it really represents. The Planck length is not the size of a particle. It is not the width of a string or the thickness of space. It is something more subtle, a boundary drawn not by experiment, but by mathematics, a point where our best descriptions of nature stop agreeing with one another. This length emerges when three fundamental constants of the universe are combined: the speed of light, the gravitational constant, and Planck's constant, Each governs a different domain of reality. Light defines the ultimate speed of cause and effect. Gravity shapes the structure of space-time. Quantum mechanics sets the scale of uncertainty and fluctuation. When these three are woven together, the result is a length, not chosen by humans, but implied by the universe itself. What makes this remarkable is not how small the number is, but what it signals. Above this scale, physics works beautifully. Space behaves smoothly. Time flows in a way we can model. Particles move, interact, and obey equations that have been tested again and again. But as distances shrink toward the Planck length, something begins to change. The familiar rules no longer fit together. Quantum mechanics demands uncertainty and fluctuation, while gravity demands structure and continuity. When both are applied at once, the mathematics begins to unravel. It is here that space itself becomes unstable. Imagine trying to draw a perfectly smooth line on paper, then zooming in endlessly. At first, the line looks continuous, but magnify it enough and the texture of the paper appears. Fibers emerge, gaps form. The idea of a perfect line dissolves into something grainy and irregular. The Planck length suggests that space-time may behave in a similar way, smooth from afar but restless and fragmented at its deepest level. Physicists sometimes describe this region as quantum foam, not because it bubbles like soap, but because it refuses to stay still. Space flickers, curvature fluctuates, tiny regions momentarily expand and collapse. Time itself becomes jittery, losing its steady flow. These fluctuations are not disturbances in space, they are disturbances of space. At this scale, asking where something is becomes deeply problematic. Position assumes a stable background, a place for things to be located. But if space is fluctuating too violently to define distances, then location loses clarity. Objects no longer sit in space in the usual sense, they exist within a shifting web of probabilities. This is why the Planck length is sometimes described as nature's smallest ruler. Not because it measures something, but because it marks the smallest interval that can be meaningfully discussed. Below it, the concept of measurement itself breaks down. What's important to understand is that this is not a failure of imagination or technology. Even if we could build instruments of infinite precision, the universe would not cooperate. Trying to probe distances smaller than the Planck length would require energies so concentrated that they would dramatically warp spacetime. The act of measurement would destroy the very structure being measured. In this sense, the Planck length is a kind of safeguard, a quiet boundary enforced by the laws of physics. It tells us that the universe does not allow unlimited resolution. There is a point beyond which the question, how small, no longer has an answer. This idea runs counter to centuries of intuition. From ancient geometry to classical mechanics, space was treated as infinitely divisible. Line could always be cut in half. A distance could always be reduced further. Infinity lived comfortably in the foundations of mathematics and physics, but the Planck length introduces a different possibility, that reality is not infinitely divisible, that there is a smallest meaningful scale, not of matter, but of space itself. This does not mean space is made of tiny blocks or beads in any simple way. The truth is likely far stranger. Some theories suggest that space-time emerges from deeper, non-spatial relationships, networks of information, or patterns of interaction that only appear spatial when viewed from afar. In such views, the Planck length is not a building block, but a resolution limit, like the smallest pixel on a screen that hides the circuitry beneath. And just as pixels disappear when you step back from a display, the graininess of space-time disappears at larger scales. The universe regains its smoothness, stars form, planets orbit, you breathe. Space feels continuous again. There is something quietly comforting in this layered structure. It suggests that the universe is not chaotic at its foundation, but carefully constrained. That beneath the apparent freedom of space lies a precise order, one that protects reality from infinite collapse and infinite fragmentation. Even time seems to respect this boundary. Associated with the Planck length is the Planck time, the smallest meaningful interval of time. Below it, The notion of before and after loses coherence. Events cannot be ordered, change cannot be tracked. Time, like space, dissolves into uncertainty. This has profound implications. If space and time themselves have limits, then the universe is not built on an infinite stage. It is built on a framework with edges, not edges you can reach, but edges you can infer. Boundaries that shape what is possible without ever needing to be touched. And yet, the Planck length is not a wall. It does not tell us that there is nothing beyond. Only that beyond this scale, our current language fails. New principles must take over. Deeper explanations must exist, ones we have not yet discovered. Physicists search for these explanations in theories of quantum gravity, attempting to unify the smooth curvature of spacetime with the restless uncertainty of the quantum world. Some propose vibrating strings. Others imagine discrete loops of space. Some suggest that spacetime itself is emergent, not fundamental at all. What they all agree on is this: the Planck length is not arbitrary. It is a signpost, a quiet message from the universe saying, this is as far as these ideas can go. As you rest now, letting these thoughts drift slowly, notice how distant this boundary feels, and yet how close it is in principle. Every atom in your body, every breath you take, every moment you experience is built upon space-time behaving smoothly above this limit. Your calm existence depends on a universe that enforces order at the smallest scales. The Planck length may be unimaginably small, but its influence is everywhere. It defines what space is allowed to be. It sets the stage for everything that unfolds upon it. And as we continue this quiet exploration, another question begins to surface. If space itself breaks down at the Planck length, what happens when we try to look even closer? And why does energy become the key that pushes reality toward its breaking point? Part 3. Why seeing smaller requires more energy. To see finer details, physics demands shorter wavelengths. Shorter wavelengths require higher energy. This simple rule has guided microscopes, particle accelerators, and human curiosity for over a century. But as energy increases, something unexpected happens. The act of observing begins to disturb the fabric of space itself. At first, this rule feels intuitive. If you want to see something small, you need a finer probe. A broad, gentle wave cannot reveal tiny features, it simply washes over them. Only tighter, faster oscillations can trace small contours. This is true whether you're using sound, water ripples, or light. Resolution always comes at a cost. In the visible world, this cost is modest. Your eyes use light with wavelengths small enough to distinguish edges, colors, and motion. A microscope improves on this by bending light more precisely, allowing you to see cells and bacteria. But even the best optical microscope reaches a limit. Atoms remain invisible. Their scale is simply too small for visible light to resolve. To go further, physics had to change its tools. Scientists learned to use particles themselves as waves. Electrons, when accelerated, behave like ripples with wavelengths far smaller than visible light. By increasing their energy, researchers could shrink those wavelengths and reveal structures at the atomic scale. Suddenly, individual atoms appeared, not as solid dots, but as probability clouds and interference patterns. This was a triumph. It confirmed a profound idea. Seeing is not about eyesight, it is about interaction. To observe something, you must disturb it with a wave or particle, and the nature of that disturbance determines what you can learn. For decades, this strategy worked beautifully. Higher energy meant shorter wavelengths. Shorter wavelengths meant finer detail. Each new accelerator peeled back another layer of reality. Quarks emerged, forces unified, patterns deepened. But quietly, beneath this success, a tension began to grow. Energy is not just a tool, it has consequences. When you concentrate energy into a smaller and smaller region of space, you are not merely shining a brighter light, you are increasing energy density. And according to the physics of gravity, energy density curves space-time. The universe does not treat observation as a passive act, it responds. At everyday scales, this response is negligible. A flashlight does not bend space in any noticeable way. even powerful laboratory experiments, barely leave a trace. But as energies climb toward extremes, the effect becomes unavoidable. Imagine trying to pinpoint a location with absolute precision. To do so, you would need an incredibly short wavelength, a probe oscillating over an unimaginably small distance. That wavelength corresponds to enormous energy. Pack that energy into such a tiny region, and gravity awakens. Space begins to curve inward. At first, the curvature is subtle, but push further and the geometry tightens. Eventually, the region becomes so warped that it forms a boundary from which nothing can escape. A horizon, a tiny black hole born not from a dying star, but from the act of trying to see too clearly. This is the moment where observation defeats itself. Beyond this point, adding more energy does not reveal smaller details, it hides them. The universe closes the door, not violently, but decisively. Information becomes trapped behind a horizon of our own making. This is not speculation in the casual sense. It emerges naturally when the principles of quantum mechanics and gravity are applied together. Each theory is extraordinarily accurate in its own domain, but when combined at extreme scales, they impose a limit. The message is simple and unsettling. There is a smallest meaningful distance, not because we lack sharper tools, but because sharper tools would destroy the space we are trying to examine. In this way, energy becomes a double-edged key. It opens doors at first, revealing deeper layers of reality, but beyond a certain point, it locks them shut. The same principle that allows us to see more eventually prevents us from seeing anything at all. There is something deeply philosophical here, though physics itself remains quiet and precise. Knowledge is not free. It has structure, limits. The universe allows itself to be known, but only within boundaries that preserve its coherence. This reframes the idea of curiosity. We often imagine that understanding comes from pushing harder, brighter, stronger. But at the deepest levels, restraint becomes just as important. Nature does not reward infinite force. It responds with silence. As you lie here now, breathing evenly, consider how gentle your perception really is. Your senses operate in a narrow, forgiving band of energies. Light touches your eyes without harming them. Sound reaches your ears without tearing them apart. The world reveals itself softly. At the smallest scales, that softness disappears. To glimpse those realms, physics must use energies so intense that reality itself begins to resist. Space is no longer a passive backdrop, it becomes an active participant. This is why particle accelerators grow ever larger, not smaller. To achieve higher energies without destroying the region of interaction, scientists spread the process out over vast distances, rings miles across, magnets carefully tuned, all to balance the need for precision against the risk of collapse. And yet, even with these precautions, there remains a fundamental ceiling. No matter how large the machine, no matter how clever the design, there comes a point where energy density cannot be increased without triggering gravitational consequences. This ceiling is not technological. It is woven into the structure of space-time itself. What's remarkable is how quietly this limit asserts itself. There is no explosion at the Planck scale, no dramatic failure, just a smooth transition from "this works" to "this no longer makes sense." Equations lose predictability, concepts blur, distance dissolves. Seeing at that point becomes meaningless, not because nothing exists, but because existence itself no longer fits within spatial language. Some physicists suspect that beyond this limit, reality is not smaller, but different. That space is not the foundation, but the result. An emergent pattern arising from deeper, non-spatial rules. In that view, energy does not reveal smaller rooms inside the universe. It reveals the scaffolding that makes rooms possible at all. If that is true, then the quest to see smaller is also a quest to understand why space exists in the first place. For now, we stand at the edge of what energy can show us, not halted by ignorance, but by design. The universe seems to say, this far and no further, at least not this way. And as we continue this calm descent into the foundations of reality, Another question gently rises. If energy bends space and hides what lies beneath, what happens at the exact moment when space itself becomes unstable and begins to flicker into something entirely new? Part 4. When observation creates gravity. Einstein taught us that energy and mass are the same thing. Concentrate enough energy into a small enough region and space-time curves. Push this too far and the region collapses inward. At extreme scales, trying to look closer may literally create a tiny black hole, hiding what you hope to see. This idea feels almost paradoxical at first. Observation is something we usually imagine as gentle, light reflecting off a surface, particles glancing past one another, information quietly arriving at our instruments. Gravity, on the other hand, feels heavy, slow, cosmic. It shapes stars and galaxies, not laboratory measurements. And yet, at the deepest levels of physics, these two ideas meet. The bridge between them is energy. In Einstein's view of the universe, gravity is not a force in the traditional sense, it is the curvature of space-time itself. Mass and energy tell space-time how to bend, and space-time tells matter how to move. This relationship is precise, mathematical, and universal. It does not care whether the energy comes from a star, a particle, or an experiment designed to observe something very small. Energy is energy. At ordinary scales, this equivalence is invisible. A beam of light does carry energy, but its gravitational influence is so tiny that it can be ignored. A laser pointer does not warp the room around it. A microscope does not bend the air it looks through. The curvature exists, but it is unimaginably small. But physics does not change its rules just because the effects are inconvenient. As you push towards smaller and smaller distances, the energy required to probe them increases dramatically. Shorter wavelengths demand higher energies. Higher energies packed into smaller regions increase energy density. And energy density is exactly what gravity responds to. At some point, the curve in space-time stops being negligible. Imagine focusing all the energy needed to probe an extremely tiny region, smaller than an atom, smaller than a nucleus, smaller than any known particle. That energy does not spread gently. It piles up. The space-time around it begins to bow inward, like fabric pulled tight by a weight placed at its center. At first, this curvature merely distorts distances. Measurements become tricky. Paths bend. Time slows slightly. But if the concentration continues, there is a threshold, a point of no return, where space-time folds in on itself. This is the birth of a horizon. A black hole is often imagined as an object, something massive, dense, and destructive. But at its core, a black hole is simply a region where space-time has curved so deeply that escape is no longer possible. Light cannot climb out. Information cannot leave. The boundary of that region, the event horizon, marks a limit not of material, but of communication. Now, consider what this means for observation. If the act of probing a small distance requires enough energy to create such a horizon, then the very attempt to observe that region seals it off. The universe responds to your curiosity by closing a curtain, not out of hostility, but out of consistency. This is not a dramatic explosion. There is no flash, no sound. From the outside, nothing remarkable happens at all. But beyond the horizon, whatever structure you hope to see is hidden forever. In this sense, gravity becomes the ultimate regulator of knowledge. It enforces a rule that no amount of cleverness can bypass. You cannot extract information from a region once it is enclosed by a horizon. The deeper you try to look, the more gravity asserts itself until observation collapses into silence. What's remarkable is how this conclusion arises naturally from combining two well-tested ideas, quantum mechanics and general relativity. Each works beautifully on its own. Quantum mechanics governs the small, relativity governs the massive. But when you attempt to apply both at once, when energy becomes both a probe and a source of gravity, their interaction imposes a limit. This is not a failure of either theory. It is a consequence of taking them seriously together. From a distance, this limit feels abstract. but there is something deeply human about it. It reminds us that the universe is not an open book with infinite pages. It has chapters that cannot be read with brute force. Some boundaries are not meant to be crossed by pushing harder. As you rest now, notice how effortless your own perception feels. You do not need to concentrate vast energy to see the room around you. The universe reveals itself freely at these scales. But that generosity fades as you descend toward its foundations. At extreme scales, even asking a question requires a cost, and that cost reshapes reality. This has led physicists to rethink what it means to understand something. Perhaps the smallest scales are not meant to be seen in the usual sense. Perhaps they are not spatial objects at all, but emergent effects, shadows cast by deeper rules that do not live in space or time. If observation creates gravity, then gravity is not just a cosmic force, it is a guardian of structure. It ensures that space-time does not tear itself apart under infinite scrutiny. It preserves coherence by limiting access. There is a quiet elegance in this. Instead of an infinite regress of smaller and smaller pieces, the universe offers a smooth surface that gives way to a boundary. Beyond that boundary, different principles must apply. Principles we have not yet learned to speak. This realization also reframes black holes themselves. They are no longer just astrophysical curiosities at the end of stars. They are hints, reminders of what happens when energy density overwhelms geometry. They are signposts pointing toward the limits of space-time. In a sense, every attempt to probe the smallest distances reenacts, on a tiny scale, the same process that shapes galaxies and governs cosmic collapse. The same rules apply everywhere. The universe does not have separate laws for curiosity and for creation. As physicists explore these ideas, they often speak softly about them, not because they are unsure, but because the implications are profound. They suggest that space is not a passive arena. It reacts, it resists, it protects its own integrity. And perhaps most striking of all, this resistance is gentle. There is no sharp wall, no sudden catastrophe, just a gradual loss of meaning. Distances blur, locations lose clarity, time stretches. And then, quietly, the questions we were asking no longer fit the reality we are probing. So when observation creates gravity, it teaches us something essential. Knowledge is relational. It depends on how we interact with the universe, not just what we ask of it. Push too hard in one direction, and reality responds by changing the terms of the conversation. As this thought settles, another question naturally forms. If gravity emerges from concentrated energy and hides the smallest scales behind horizons, what does space-time itself look like just before it collapses in that restless region where it begins to flicker and lose its smooth shape? Part 5. The moment space becomes unstable. As distance shrinks toward the Planck length, space-time no longer behaves like a calm surface. It trembles, fluctuates, folds in on itself. Physicists call this quantum foam, a restless, jittering state where space and time lose their smooth continuity. To picture this, it helps to let go of the idea that space is something solid or fixed. At human scales, space feels dependable. Distances remain constant, directions make sense. You can move from one place to another without the ground of reality shifting beneath you. But this calm is an illusion born of scale. Far below atoms, far below anything we can touch or see, space behaves very differently. At these depths, uncertainty dominates. Quantum mechanics tells us that nothing can ever be perfectly still. Energy fluctuates even in what we call empty space. Fields vibrate, particles appear and vanish. At larger scales, these fluctuations average out into stability. But as you move closer to the Planck length, they stop canceling each other. They begin to shape reality itself. Space starts to flicker. Imagine looking at the surface of a calm lake from far away. It appears smooth, almost glass-like. But as you approach, ripples become visible. Get closer still, and you see waves colliding, overlapping, rising and falling. The idea of a single flat surface dissolves into motion. Quantum foam is something like that, except the surface is space-time itself. In this regime, Space is no longer a continuous backdrop. It is active, dynamic. It seethes with microscopic distortions where geometry twists and snaps back, never settling long enough to be defined. Distances stretch and shrink unpredictably. Directions lose their stability. Even the notion of here becomes uncertain. Time suffers the same fate. At ordinary scales, time flows smoothly, one moment following another. But near the Planck scale, that flow fractures. Quantum fluctuations disrupt the ordering of events. Cause and effect blur. Moments overlap. The clean sequence of before and after no longer holds. This is not chaos in the everyday sense. It is not random destruction. It is something subtler, a regime where our usual concepts simply stop applying. Space and time are still present in some form, but not in the smooth, continuous way we are used to. Physicists call this quantum foam not because it looks like bubbles, but because it shares a quality of constant, restless change. Tiny regions of space-time briefly pinch off and reconnect. Curvature fluctuates wildly. For an instant, a microscopic region may resemble a black hole, only to dissolve again before anything can fall in. These fluctuations are incredibly short-lived, lasting only for Planck time intervals. They are not events you could observe directly, even in principle. They exist beneath observation itself, shaping the stage on which all observable phenomena occur. What's striking is that this instability is not added on top of spacetime. It is spacetime at this scale. There is no calm structure beneath it. The foam is the foundation. This realization forces a quiet shift in perspective. We often imagine that the universe becomes simpler as we go smaller. Fewer particles, fewer interactions, fewer distractions. But the opposite may be true. At the smallest scales, reality may be most complex, most dynamic, most alive with activity. The smooth geometry we rely on, straight lines, fixed distances, stable durations, may be an emergent illusion, a statistical average of deeper fluctuations that never truly settle down. This idea has profound consequences. If spacetime itself is unstable at the Planck scale, then the universe is not built on a rigid framework. It is built on motion, on relationships, on probabilities that solidify only when viewed from afar. Stability is something that emerges, not something that exists at the bottom. That emergence is what allows stars to form, planets to orbit, and you to rest comfortably without feeling the universe shiver beneath you. The foam averages out, the fluctuations cancel, calm appears, but it is always there underneath. Some physicists suspect that quantum foam is a sign that spacetime is not fundamental at all, that it arises from something deeper, networks of interactions, flows of information, or rules that do not involve space or time in the usual sense. In this view, space is like a shadow cast by deeper processes we do not yet fully understand. At the Planck scale, that shadow breaks apart. What makes this especially humbling is that no amount of technological progress can smooth the foam away. It is not noise that can be filtered out. It is not error. It is the signal itself. The closer you look, the louder it becomes. And yet, this instability does not threaten the universe. Quite the opposite. It may be what allows the universe to exist at all. The foam provides flexibility. It allows spacetime to respond to energy, to curve, to stretch, to evolve. Without it, gravity would have no medium to act upon. Change would be impossible. In a sense, quantum foam is the universe breathing at its smallest scale. As you lie here now, breathing slowly yourself, it's worth noticing the parallel. Your breath is calm on the surface, rhythmic and steady. But inside your body, countless microscopic processes are in motion. Molecules colliding, ions flowing, signals firing. Stability arises not from stillness, but from balance. The universe works the same way. At the Planck scale, balance has not yet emerged. The motions are too small, too fast, too intense. Space-time has not settled into geometry. It is still negotiating its own structure. This is why physics becomes quiet and cautious here. Equations lose their predictive power. Words like distance and duration must be used gently, if at all. we are no longer describing objects moving through space. We are describing space itself, struggling to define what movement means. There is something deeply peaceful in accepting this limit. It reminds us that not everything needs to be sharply defined, that ambiguity is not a flaw, but a feature of reality at its most fundamental level. The universe does not demand infinite precision, it allows softness at its core. And yet, the foam is not the end of the story. Even within this instability, patterns may exist, rules may apply, new forms of order may emerge, ones we are only beginning to glimpse. As physicists explore theories that attempt to describe this realm, they do so knowing that they are approaching the edge of language itself. The foam resists description, not because it is unknowable, but because it lives beyond the concepts we inherited from a smooth world. So when space becomes unstable, it is not breaking. It is revealing its true nature. And as we continue this quiet journey deeper still, another question gently waits for us. If space-time flickers and loses continuity at the smallest scales, could it be that space itself is made of discrete pieces, like pixels, rather than a smooth continuum? Part 6. Why space may be made of pixels. Some theories suggest space is not continuous at all, but granular, composed of indivisible units like pixels on a screen. Just as you cannot zoom infinitely into a digital image, you may not be able to zoom infinitely into reality. At human scales, space feels smooth and uninterrupted. You can move your hand slowly through the air and feel no resistance, no stepping from one location to the next. Distance feels like a flowing continuum, something that can always be divided into smaller and smaller parts. This intuition has shaped geometry, navigation, architecture, and physics for thousands of years. But intuition is shaped by scale. When physicists began examining the universe at its smallest extremes, they encountered a subtle but persistent hint that this smoothness might be an illusion, much like the illusion of a flawless image on a screen. From far away, the picture looks continuous. Step closer, and structure emerges. Pixels appear. There's a finest resolution beyond which detail does not increase. The idea that space itself might have a similar resolution limit is both radical and strangely familiar. In everyday technology, pixels are not flaws. They are the fundamental units that make images possible. A digital photograph is not a continuous smear of color. It is a grid of discrete points, each carrying a finite amount of information. You can zoom in only so far before the image stops revealing new detail and begins repeating itself in blocks. If space is built in a similar way, then the Planck length may represent its pixel size, the smallest unit of distance that can exist meaningfully. This does not mean space is literally a grid like graph paper. Nature rarely chooses simple patterns. Instead, these pixels may be abstract, dynamic, and relational. They might not sit next to each other in neat rows. They may not even exist in space, but rather define space through their connections. The key idea is discreteness. For much of physics, discreteness has been a familiar concept. Energy comes in quanta. Electric charge is quantized. Angular momentum appears in discrete steps. Even light, once thought to be a smooth wave, arrives in individual packets called photons. Again and again, nature has revealed that what looks continuous from afar is made of indivisible units underneath. So it is not unreasonable to suspect that space itself follows this pattern. Several approaches to quantum gravity take this possibility seriously. They suggest that space-time is not fundamental, but emergent, built from smaller, non-spatial elements whose relationships give rise to geometry at larger scales. In these views, distance is not something that exists on its own. It is something that happens when these elements interact in particular ways. This shifts the question entirely. Instead of asking, how small can space be? We begin asking, what gives rise to space at all? The pixel analogy helps here, not because it is exact, but because it captures the idea of a limit to resolution. You can describe an image at high resolution, but below the pixel scale, the concept of image no longer applies. Similarly, if space is granular, then below a certain scale, the concept of distance simply stops making sense. not because nothing exists, but because what exists is not spatial in the way we understand. This has deep consequences for how we imagine the universe. In a continuous space, motion is smooth. Objects pass through every intermediate point. Paths are well-defined curves. In a granular space, motion becomes something else, a sequence of transitions, a hopping from one configuration to another. At large scales, this hopping averages out into smooth motion, just as individual pixels blend into a continuous image when viewed from afar. From this perspective, the calm geometry of everyday life is an emergent illusion, a large-scale approximation of something far more discrete underneath. There is a quiet elegance in this idea. It suggests that the universe is economical. It does not require infinite detail to function. It builds complexity from simple, finite components, then allows that complexity to appear smooth when viewed at the right scale. This may also explain why the universe enforces a smallest distance. If space has a fundamental unit, then trying to divide it further is like trying to split a pixel in half. The question itself becomes ill-posed. There is no smaller answer to find. Importantly, this discreteness does not necessarily imply rigidity. Space may still fluctuate, stretch, and evolve. The pixels may rearrange themselves constantly. They may flicker in and out of existence. The granularity does not make space static. It makes it dynamic at its foundation. Time may share this property as well. Just as space might be made of discrete units, time may proceed in indivisible steps. Below a certain interval, the flow of time loses coherence. Events cannot be ordered. Cause and effect blur. Like space, time may be smooth only when viewed from far enough away. Together, these ideas paint a picture of a universe that is not infinitely sharp, but softly resolved. One that does not allow infinite scrutiny, not out of secrecy, but out of structure. As you lie here now, notice how restful this thought can be. The universe is not fragile under endless division. It is stable because it has limits. It knows how much detail is enough. There is also something humbling in this. Human mathematics often leans toward infinity. Infinite precision, infinite divisibility, infinite extension. But nature may be more modest. It may favor finiteness, not as a constraint, but as a foundation. If space is pixelated, then geometry itself is an approximation. Straight lines, perfect circles, exact distances, these are emergent concepts, useful and accurate at large scales, but not fundamental. At the deepest level, reality may be relational rather than spatial, defined by how fundamental elements influence one another rather than where they are located. This perspective aligns quietly with earlier insights. We learned that energy cannot probe arbitrarily small distances without collapsing space-time. We learned that observation itself reshapes geometry. Now we see a possible reason why. Space may not be something that can be sliced endlessly. It may be built from indivisible pieces that refuse further division. The pixel analogy also reframes emptiness. What we call empty space may not be empty at all. It may be filled with these fundamental units, constantly interacting, exchanging information, forming the background upon which particles and forces appear. Vacuum becomes structure. Nothingness becomes activity. This does not make the universe less mysterious. It deepens the mystery. If space is not fundamental, then what is? What are these underlying elements? What rules govern their interactions? How does smooth reality emerge so reliably from something discrete and restless? These are open questions, quiet ones, questions that physicists approach with patience rather than certainty, and that patience feels appropriate. We are not racing toward an answer. We are drifting toward understanding. As this segment draws to a gentle pause, one more question naturally arises. If space is made of indivisible units, and smoothness is only an illusion at large scales, what happens when those units themselves begin to fluctuate violently, when space no longer even resembles a stable grid, but starts to dissolve into something far less orderly? Part 7. Time begins to fracture. Two space and time are woven together. When space breaks down, time follows. At extreme scales, time may stop flowing smoothly. Events no longer follow a clear before and after. Cause and effect blur into probability. For most of human experience, time feels steady and reliable. Seconds follow seconds. Nights give way to mornings. You can close your eyes, count a few breaths, and trust that the world will still be there when you open them again. This intuition runs deep. It feels almost biological. Time seems like the one thing that never hesitates. But physics tells a quieter, stranger story. Ever since Einstein, we have known that time is not an independent backdrop ticking away the same everywhere. It is bound to space, woven into a single structure called space-time. Motion stretches it, gravity slows it, speed and mass shape how quickly it flows. Time, in other words, is already flexible, even in the familiar universe you inhabit. At ordinary scales, this flexibility is subtle. Clocks on satellites tick slightly faster than clocks on Earth. Astronauts age a little more slowly in orbit. These effects are tiny, but they are real, measured, and essential to modern technology. Time is already uneven. We simply don't notice. But as we descend toward the smallest scales of reality, this unevenness grows dramatic. When space becomes unstable near the Planck length, time cannot remain intact. The smooth sequence of moments begins to dissolve. Instead of flowing like a river, time starts to behave more like a flickering signal, jittery, discontinuous, uncertain. One reason for this lies in how quantum mechanics treats change. At very small scales, systems do not evolve smoothly. They jump, they fluctuate, they exist in superpositions of states where outcomes are not decided until interactions occur. In this domain, time does not act as a clean parameter guiding motion. It becomes tangled with probability. Now add gravity to this picture. Gravity curves space-time. Near extreme concentrations of energy, time slows dramatically. At the edge of a black hole, for example, time nearly stops relative to a distant observer. But near the Planck scale, this curvature is not smooth. It fluctuates wildly. Tiny regions of space-time bend and unbend, stretch and collapse in unpredictable ways. When this happens, the idea of a single global clock loses meaning. To say that one event happens before another assumes that time can be ordered, that moments line up in a consistent sequence. But if space-time itself is fluctuating, that sequence becomes ambiguous. Different paths through space-time may disagree on the order of events. Cause and effect, once reliable companions, drift apart. This does not mean chaos in the everyday sense. It means that the universe at these scales does not commit to a single history. Instead, multiple possibilities coexist, weighted by probability, until interactions force a resolution. Time, in this view, is not a universal flow. It is an emergent feature, something that arises when space-time is smooth enough, stable enough, and large enough for sequences to make sense. Below that threshold, time fractures. Physicists sometimes describe this as the breakdown of classical causality, not because causes disappear, but because the framework that orders them fails. Without a stable notion of earlier and later, the language of cause and effect becomes approximate rather than exact. This is deeply unsettling because causality feels fundamental. It underlies memory, responsibility, and meaning. But physics does not promise comfort, it promises consistency. At the smallest scales, consistency demands letting go of familiar structures. Consider how time is measured. A second is defined by a specific number of oscillations of radiation in an atom. That definition assumes stability, a repeating pattern that can be counted. But near the Planck scale, such regularity may not exist. Oscillations blur, intervals fluctuate. There is no steady rhythm to anchor a clock. In such a regime, asking, "How long did this take?" may be as meaningless as asking, "Where did this happen?" Both questions rely on space-time being well-behaved. When it isn't, those concepts dissolve together. This has led some physicists to suggest that time is not fundamental at all, that at the deepest level, the universe does not evolve in time. Instead, it exists as a network of relationships, correlations between states, and time emerges only when those relationships are coarse-grained into a smoother picture. From this perspective, time is like temperature. Temperature feels fundamental, but it only emerges when many particles interact. At the level of individual molecules, temperature does not exist. Likewise, time may only emerge when space-time is large enough and stable enough for sequences to matter. There is something almost soothing in this idea. It suggests that the relentless ticking you feel is not imposed from the outside, but generated locally. Time flows where conditions allow it to flow. It slows where gravity deepens. It fractures where space-time becomes restless. And it disappears where change itself cannot be ordered. As you lie here now, time feels gentle, unthreatening. Each breath follows the last. That calm flow is not guaranteed everywhere in the universe. It is a privilege of scale. At the Planck level, even the concept of now becomes ambiguous. Different observers, following different quantum paths, may not agree on what exists at a given moment. Reality does not settle into a single present. It hovers among possibilities. This does not mean that the universe is unreal or ill-defined. It means that our familiar narrative, one thing happens, then another, is a simplified story told at large scales. A useful story, a comforting one, but not the deepest truth. When time fractures, physics does not replace it with chaos, but with mathematics. Probabilities replace certainties, amplitudes replace trajectories. The universe remains lawful, but its laws speak a quieter, more abstract language. This is one reason why unifying gravity and quantum mechanics has proven so difficult. Quantum theory assumes time exists as a background parameter. General relativity makes time dynamic and malleable. At the smallest scales, both assumptions fail. Time is neither fixed nor smoothly dynamic. It becomes something else entirely. Perhaps time is not something the universe moves through, but something that emerges within it, a pattern arising from stability, not a fundamental ingredient. If so, then the fracturing of time at small scales is not a breakdown, but a return to something more basic. A realm where the universe does not march forward, but simply exists in a vast space of potential relationships. And when space-time smooths out, when distances grow large, when energy densities fall, when fluctuations average away, time reappears. Flow resumes, history forms, memory becomes possible. This makes your current experience all the more remarkable. Right now, time is flowing for you, gently, reliably. That flow rests on a delicate balance, one maintained by the large-scale smoothness of space-time. Beneath it lies a restless foundation where time itself cannot decide how to behave. As this thought settles, another question quietly presents itself. If space can be granular and time can fracture, then what is reality truly made of beneath these familiar dimensions? And could something deeper be giving rise to both space and time together? Part 8. The failure of our greatest theories. Quantum mechanics governs the very small. General relativity governs the very massive. Both are stunningly accurate, but at the Planck scale, they contradict each other. This is not a gap in technology. It is a gap in understanding. For most of modern science, this contradiction was invisible. The universe is generous that way. It separates its extremes. Quantum mechanics rules atoms, particles, and probabilities, where gravity is so weak it can be ignored. General relativity rules planets, stars, and galaxies, where quantum effects wash out into smooth averages. Each theory works flawlessly where the other remains silent. For decades, this division felt natural. Physicists learned where to apply each framework. If you wanted to understand how electrons behave in a semiconductor, you used quantum mechanics. If you wanted to predict the orbit of a planet or the bending of light near a star, you used relativity. The two theories coexisted peacefully, like neighboring languages spoken in different regions of reality. But deep down, everyone knew this peace was fragile. The universe does not come with separate instruction manuals for the small and the large. There is only one reality. Somewhere, somehow, these two descriptions must meet. And when physicists followed nature all the way down to the smallest meaningful scales, the Planck scale, they found not harmony, but conflict. Quantum mechanics insists that nothing is ever completely still. Fields fluctuate, particles pop in and out of existence. Uncertainty is not a limitation of knowledge, but a fundamental feature of nature. Even empty space is alive with activity, a seething background of virtual processes. General relativity, on the other hand, treats space-time as a smooth, continuous geometry. Mass and energy curve it gently. Distances and durations are well defined. The equations assume that space-time can be divided as finely as needed without ever breaking. At everyday scales, these assumptions coexist without trouble. But as distance shrinks toward the Planck length, the demands of each theory become impossible to reconcile. Quantum mechanics says space-time should fluctuate violently at tiny scales. General relativity says space-time must remain smooth enough to define curvature. One demands jitter, the other demands continuity. When both are applied at once, the mathematics stops making sense. The equations do not merely become difficult, they become contradictory. This is what physicists mean when they say our greatest theories fail. Not that they are wrong in their domains, they are extraordinarily right, but that they cannot both be true in the same place at the same time at the deepest level of reality. This failure is subtle. There is no experiment that suddenly explodes or refuses to work. Instead, the breakdown appears when we ask certain questions. What is the geometry of space-time at the smallest scale? What happens inside a black hole? What was the universe like at the very first instant of the Big Bang? When we try to answer these questions, the tools we trust most give incompatible answers. Quantum mechanics predicts infinite fluctuations of energy at arbitrarily small scales. General relativity responds by predicting infinite curvature, singularities where space-time tears itself apart. Infinity appears in the equations not as a sign of something truly infinite, but as a warning that the theory has been pushed beyond its limits. Physicists take infinities seriously, not as mysteries to admire, but as signals that something is missing. Throughout the history of science, infinities have always pointed to deeper structure. When classical physics predicted infinite energy from a hot object, quantum theory resolved it. When Newton's gravity allowed infinite density at a point, relativity reframed gravity as geometry. Each time, infinities marked the edge of an old framework. The Planck scale is such an edge. What makes this especially unsettling is that both theories involved have passed every experimental test thrown at them. Quantum mechanics predicts particle behavior to astonishing precision. Relativity predicts gravitational phenomena with equal accuracy. They are not approximations waiting to be replaced, they are pillars. And yet, they cannot both be fundamental. This realization has reshaped how physicists think about progress. The problem is not to make better measurements or build larger machines. Even if we could probe the Planck scale directly, our theories would not know how to interpret the results. The issue lies deeper, in the language we use to describe reality. It suggests that space-time itself, the stage on which both theories are written, may not be fundamental. Perhaps space-time is emergent, like temperature. Temperature feels fundamental, but it emerges from the motion of countless particles. At small enough scales, temperature ceases to exist as a meaningful concept. In the same way, space and time may emerge from deeper, non-spatial rules, rules that quantum mechanics and relativity each approximate from opposite sides. If this is true, then their failure at the Planck scale is not a disaster. It is a clue. It tells us that we are using the wrong concepts, that geometry and probability, curvature and uncertainty are shadows cast by something more basic, something that does not look like space or time at all. This is why physicists search for a theory of quantum gravity, not because gravity is poorly understood, but because understanding gravity at the quantum level forces us to rethink everything else. It demands a framework where space-time can fluctuate without becoming meaningless and where uncertainty does not destroy structure. Many ideas have been proposed. Some imagine that space is woven from tiny loops. Others suggest vibrating strings existing in higher dimensions. Some propose that reality is built from networks of information, where space emerges from relationships rather than coordinates. What all these ideas share is humility. They begin with the admission that our most successful descriptions of the universe are incomplete, that the deepest layer of reality may not resemble anything we directly experience, that our intuition shaped by macroscopic life, may fail us at the foundations. As you lie here now, letting these ideas drift gently, there is no need to resolve them. Physics itself has not yet done so. The important thing is not the answer, but the realization that the universe still holds unanswered questions at its core. There's something calming in that. Despite centuries of progress, despite equations that predict eclipses and electronics and cosmic expansion, reality retains a quiet mystery. Not because it is chaotic, but because it is layered, each layer revealing itself only when the previous one fails. The failure of our greatest theories is not an ending. It is a threshold, a reminder that understanding grows not in straight lines, but in gentle revolutions. Each time we reach a limit, we are invited, patiently, to rethink our assumptions. At the Planck scale, quantum mechanics and general relativity both whisper the same message. This is not the whole story. And as we continue this quiet journey forward, another question naturally unfolds. If our deepest theories fail because space-time itself may not be fundamental, what is it that the universe is really made of beneath space, beneath time, beneath geometry itself? Part 9. Why the universe protects its secrets. No matter how powerful our instruments become, the universe seems to enforce a boundary. Beyond a certain point, information cannot escape. Not because we lack tools, but because reality itself refuses to reveal more. This refusal is not abrupt. It does not announce itself with alarms or broken machines. It arrives quietly, as limits usually do. Equations begin to soften at the edges. Predictions lose their sharpness. Questions that once made sense start to feel slightly misaligned, as though they were written for a different kind of world. For most of human history, the universe appeared generous. Each time curiosity pressed forward, nature responded with another layer of explanation. Planets moved according to laws, atoms revealed internal structure, light behaved like a wave, then like a particle, then like something stranger still. Discovery followed discovery in a steady, reassuring rhythm. It felt natural to assume that this generosity would continue forever, but as physics reached deeper into reality, something unexpected emerged. Not another hidden layer, but a boundary that seemed woven into the universe itself. A point beyond which information could not be retrieved, no matter how carefully or cleverly one tried. This idea challenges a deeply rooted belief that the universe is fully knowable in principle, given enough time and ingenuity. Instead, it suggests that reality may be structured to withhold certain truths, not out of malice, but out of necessity. To understand why, it helps to think about information itself. Information is not abstract, it is physical. It must be carried by particles, waves, or fields. It must travel through space and persist through time. Every bit of knowledge, every measurement, every observation depends on information being able to move from where something happens to where it can be known. And this movement is not guaranteed. In some regions of the universe, information simply cannot escape. Not because it is blocked by walls or shields, but because the geometry of space prevents it. Horizons form. Boundaries appear where paths point inward no matter which way you try to go. Beyond these horizons, events may occur, but they can never influence the outside world. This is not a technical limitation, it is a geometric one. The most familiar example of such a boundary is a black hole horizon, but the principle is broader. Whenever energy becomes concentrated enough to curve spacetime severely, horizons emerge, and horizons are absolute. They do not weaken with better instruments. They do not dissolve with patience. They simply exist. What makes this so striking is that horizons are not objects. They are relationships between space, time, and motion. They define what can be known, not by force, but by structure. They are the universe's way of saying that certain questions cannot be answered from certain vantage points. At the smallest scales, this same principle appears again. As you try to extract information from ever tinier regions, the energy required to do so increases. That energy alters spacetime. Push far. Enough, and a microscopic horizon forms, one that seals off the very region you hope to understand. The information is not destroyed. it is merely rendered inaccessible. From the outside, it might as well not exist. This is why the universe seems to protect its secrets, not actively, not intentionally, but inevitably. The same laws that allow information to flow also define where it must stop. There is no separate rule for curiosity. The universe does not make exceptions. This can feel unsettling at first. We are used to thinking of knowledge as something that accumulates without limit, that each generation stands higher than the last, seeing farther simply because it has climbed higher. But the universe suggests a different picture, one where vision improves only up to a point and then fades not into darkness, but into ambiguity. There is a quiet humility in this. It reminds us that understanding is not the same as possession. We can describe patterns, predict outcomes, and build remarkably accurate models of the world, all without ever accessing its deepest layer directly. Perhaps that layer does not need to be accessed to be meaningful. Consider how much of your own experience is inferred rather than seen. You do not feel individual atoms. You do not sense space-time curvature. Yet you live comfortably within their effects. You trust the structure beneath you without needing to examine it. The universe may be asking for a similar trust at its foundations. Some physicists suspect that these boundaries are not flaws, but features, that without them, reality would be unstable. If information could be extracted from arbitrarily small regions, space-time might fragment endlessly. Energy densities would spike uncontrollably. The coherence that allows stars, planets, and lives to exist might never form. In this view, horizons are stabilizers. They preserve order by limiting access. They ensure that not everything can influence everything else. They create separation, locality, and structure. There is something almost protective about this idea, as though the universe maintains its integrity by setting gentle but firm limits on inquiry. Not because it fears being known, but because being fully exposed would unravel it. As you rest here now, letting your thoughts slow, it may help to notice how many boundaries already shape your life. You cannot hear every sound. You cannot see every color. You cannot remember every moment. These limits do not diminish your experience. They make it navigable. Perhaps cosmic limits serve a similar role. When physics reaches a point where information cannot escape, it does not signal defeat. It signals a transition. A reminder that our current language, built on space, time, and measurement, may no longer apply. That deeper descriptions may exist, but they may not be accessible in the way we expect. This reframes the search for knowledge. Instead of asking how to push past the boundary, we begin asking why the boundary exists at all, what role it plays, what it preserves. And in that shift, something subtle happens. The boundary becomes not an obstacle, but a clue. It tells us that reality is relational, that what can be known depends on where you stand and how you interact. That information is not absolute, but contextual. That some truths exist only within certain frames and vanish when viewed from others. There is a quiet peace in accepting this. You do not need to know everything to belong in the universe. You do not need to see its deepest layer to be part of its unfolding. Your existence is already woven into its structure, whether or not its final secrets are revealed. The universe protects its secrets not by hiding them, but by shaping the conditions under which knowing is possible. It invites understanding, but not ownership. Exploration, but not domination. And as this realization settles, another question gently emerges. If information itself is limited by the structure of space and time, what does that say about reality beneath those structures, where space, time, and information may no longer exist in familiar forms at all? Part 10. Did space exist before the universe began? If space has a smallest unit, then it may also have a beginning. At the earliest moments after the Big Bang, space may not have existed at all, only energy, fluctuations, and potential waiting to become geometry. This idea gently unsettles one of our deepest assumptions. We are used to imagining the universe as something that expands into space, as if space were an empty container waiting to be filled. Galaxies drift apart, distances stretch, and the cosmos grows larger over time. But modern physics suggests something quieter and stranger. Space itself may be part of what emerged, not the stage, but the actor. When cosmologists trace the universe backward, they do not see matter moving through a fixed backdrop. They see space-time itself changing. Distances shrink, time intervals shorten, the entire fabric compresses. As this rewind approaches the beginning, familiar concepts begin to strain. Eventually, they stop working altogether. In the earliest fractions of a second after the Big Bang, the universe was unimaginably hot and dense. Energy dominated everything. Particles, as we know them, could not exist. Forces we now distinguish, gravity, electromagnetism, the nuclear forces, were likely unified into something simpler and more symmetrical. In this state, space may not have been a smooth expanse at all. It may not have been space yet. The equations that describe the early universe suggest that geometry itself was unstable. Curvature fluctuated wildly. Distances were not fixed. Directions may not have been meaningful. The universe was less like a place and more like a process, a constant reshaping driven by energy and change. This raises a subtle but profound question. If space was still forming, what does before even mean? Time after all is woven into space. In Einstein's framework, you cannot separate the two. If space had not yet settled into existence, then time may not have flowed in the way we imagine either. The idea of a moment before the universe becomes ambiguous. Not wrong, just undefined. Some physicists describe this early phase not as a beginning in time, but as the beginning of time, a transition from a state where temporal order did not yet apply into one where cause and effect could unfold smoothly. In this view, asking what happened before the universe is like asking what lies north of the North Pole. The question assumes a direction that no longer exists. This perspective changes how we think about origins. Instead of a singular event exploding into empty space, we have a gradual emergence of structure. Energy cools, symmetry breaks, distinctions appear, space crystallizes into something that can be measured. Time begins to flow in a consistent direction, geometry is born. There's something deeply calm about this picture. It removes the drama of creation and replaces it with a quiet unfolding. The universe does not arrive fully formed, it settles into itself. Modern theories of quantum gravity take this idea seriously. They suggest that space-time may be an emergent phenomenon, not fundamental, but derived. Just as temperature emerges from the motion of particles, space may emerge from deeper, non-spatial interactions. At high energies, those interactions dominate. At lower energies, space becomes a useful description. In this view, the Big Bang is not a point in space, but a limit of description, a boundary where our usual concepts dissolve. Beyond it, there may be no distances to speak of, only relationships, probabilities, and transformations. This also reframes cosmic expansion. Space is not expanding into anything. It is expanding because its own rules are changing. The metric that defines distance evolves. Galaxies drift apart not because they are moving through space, but because the space between them is becoming more spacious. Early on, this expansion may have been violent. A brief period of rapid growth, often called inflation, could have smoothed out irregularities and stretched tiny quantum fluctuations into the seeds of galaxies. During this phase, space-time itself was still settling, still learning how to behave. Before that, if before applies, there may have been no notion of distance at all. This possibility challenges our intuition, but it also offers clarity. If space has a smallest unit, then it cannot be meaningfully subdivided forever. And if it cannot be subdivided forever, then tracing it backward must eventually lead to a point where subdivision stops entirely. A phase where geometry itself is undefined, not destroyed, undefined. As you rest with this idea, notice how gently it shifts perspective. The universe is not something that appeared inside space. Space is something the universe learned how to be. This also means that the question of what existed outside the universe may be misplaced. Outside implies space, but if space itself emerged with the universe, then there is no outside to speak of. The universe is not an object with edges. It is the origin of edges. There is humility in this realization. It reminds us that our language evolved to describe experiences within space and time. When we push beyond those boundaries, language stretches thin. Metaphors replace definitions. Silence becomes as meaningful as explanation. Physicists are careful here. They do not claim certainty. They follow equations as far as they go, then stop where the equations lose meaning. That stopping point is not a failure. It is information. It tells us where new ideas are needed. Some speculate that the universe may have undergone transitions, from a non-spatial phase to a spatial one, from timelessness to time. Others explore the possibility of multiple phases, cycles, or even prior universes governed by different rules. These ideas remain tentative, mathematical, and restrained. What they share is a willingness to let go of assumptions. As you breathe slowly now, imagine the universe not as a sudden flash, but as a gentle condensation. From a formless energy, patterns begin to stabilize, relationships repeat, geometry takes hold, distances become meaningful, time begins to flow, stars will one day form, planets will orbit, minds will emerge that wonder how it all began, and all of it rests on a phase where space itself was still becoming. This perspective also softens the mystery. Instead of demanding an answer to what came before, it invites a different kind of curiosity, one that listens rather than insists. The universe may not owe us a narrative that fits our intuitions. It offers something quieter, coherence within its own rules. So did space exist before the universe began? According to our best understanding, space did not precede the universe. It arose with it. Or perhaps more gently, it condensed out of something deeper, something not spatial, not temporal, but capable of becoming both. And as we continue this calm exploration, another question waits just ahead. If space and time themselves emerged from deeper principles, what exactly failed in our greatest theories when we tried to describe that transition? And why do those failures point towards something entirely new? Part 11. Black holes as natural Planck laboratories. At the center of black holes, matter is crushed beyond comprehension. These regions may naturally reach Planck scale conditions, where space dissolves and known physics fails, turning black holes into silent laboratories of broken reality. From far away, a black hole appears deceptively simple. It has mass, spin, and charge. It bends the paths of nearby stars and light with quiet authority. Nothing dramatic seems to happen at its boundary. An object crossing the event horizon does not explode or shatter from an outside perspective. The black hole simply absorbs it, adding its energy to the curvature of space-time. But beneath that calm exterior lies the most extreme environment the universe can produce. Black holes form when gravity wins completely. When all known forces that resist collapse, pressure, heat, quantum effects, are overwhelmed. In massive stars, this happens at the end of their lives, when nuclear fuel runs out and the core can no longer support itself. The collapse continues inward, faster and faster, until space-time curves so deeply that an event horizon forms. Once that horizon exists, something remarkable happens. The interior of the black hole is no longer just a region of space. It becomes a one-way direction in time. Moving inward is no longer a choice. It is as inevitable as the passage of seconds. And somewhere deep inside, according to general relativity, all the mass collapses toward a single point, a singularity. A location where density becomes infinite, curvature becomes infinite, and the equations of physics break down entirely. Physicists are careful with that word, singularity. It does not necessarily describe a real physical object. It describes a place where our theories stop working, a sign that something fundamental is missing from our understanding. What makes black holes so important is that they may push nature all the way to the Planck scale without any human interference. In particle accelerators, reaching Planck energies is effectively impossible. The energies required are far beyond anything we can generate or contain. But gravity, given enough mass and time, does not face that limitation. It concentrates energy naturally, relentlessly, patiently. As matter falls inward, its energy density increases. Distances shrink, time slows, space warps more and more violently. Eventually, the scales involved approach those where quantum mechanics and gravity must both apply at once. This is precisely the regime where our current theories fail. In that sense, black holes are not just cosmic curiosities. They are the universe's own experiments, places where the deepest laws of reality are tested to their limits. They are natural Planck laboratories, running continuously for billions of years. What happens there is unknown. General relativity predicts a singularity, a point of infinite density. Quantum mechanics, however, strongly resists infinities. In every other context, infinities signal that a theory is incomplete. That suggests that inside black holes, a new description of reality must take over. Perhaps spacetime becomes quantized. Perhaps it dissolves into discrete units. Perhaps the concept of space itself ceases to exist, replaced by something more abstract. From the outside, we cannot see this directly. The event horizon blocks all information, but subtle clues may leak out in indirect ways. One of the most profound insights of modern physics is that black holes are not entirely black. Quantum effects near the horizon allow them to emit radiation, now known as Hawking radiation. This radiation is incredibly faint for large black holes, but it carries a stunning implication. Black holes can slowly lose mass and eventually evaporate. This creates a deep puzzle. If a black hole evaporates, what happens to the information about everything that fell into it? Quantum mechanics insists that information is never destroyed. General relativity, taken literally, suggests that information disappears behind the horizon forever. This conflict, the black hole information paradox, has driven decades of research, and at its heart lies the Planck scale. Many proposed solutions suggest that the resolution depends on what spacetime does at the smallest distances. Some ideas propose that information is stored on the event horizon itself, encoded in Planck scale degrees of freedom. Others suggest that spacetime inside the black hole connects to other regions, or that singularities are replaced by quantum structures. In all cases, black holes force us to confront the limits of our concepts. They challenge the idea that space is continuous. They challenge the idea that time flows smoothly. They even challenge the idea that inside and outside are well-defined notions. From a human perspective, there is something almost meditative about this. The most violent objects in the universe become, at their core, places of profound silence, regions where the universe stops explaining itself in familiar terms. As you rest now, imagine drifting far from any star, watching a black hole from a safe distance. You see matter spiral in, glowing briefly before fading from view. You see light bend and curve, tracing the shape of invisible geometry. But beyond the horizon, there is nothing to see. Only inference, only equations, only unanswered questions. And yet those unanswered questions are not failures, they are invitations. They suggest that spacetime, which feels so solid and reliable in daily life, is not fundamental. It may be emergent, a large-scale effect arising from deeper Planck-scale rules. Black holes may peel back that illusion, revealing the raw scaffolding beneath. Some physicists suspect that inside black holes, space becomes discrete, granular, or network-like. Others imagine that spacetime undergoes a phase transition, like water freezing into ice, but at the level of geometry itself. Still, others propose that black holes connect to other regions of spacetime in ways we do not yet understand. What all these ideas share is humility. Black holes remind us that our theories are approximations, extremely good ones, tested and confirmed again and again, but not final. There are regimes where they no longer apply, and those regimes are not hypothetical. They exist quietly all across the universe. Every galaxy harbors a supermassive black hole at its center, millions of solar masses compressed into regions smaller than our solar system. If Planck-scale physics plays out anywhere, it plays out there. In this way, the universe does not hide its deepest secrets entirely. It places them at the hearts of galaxies, wrapped in horizons, running experiments we cannot yet read, but whose consequences shape cosmic evolution itself. Black holes influence how galaxies form, how stars move, how matter distributes itself on the largest scales. Even without knowing their interiors, we feel their presence everywhere. And perhaps that is fitting. The deepest truths of reality may not be meant to be directly observed, but inferred slowly, patiently through their effects, through shadows, through boundaries, through silence. As we continue this quiet journey, one question remains softly open. If black holes push space-time to its breaking point, what does that tell us about reality itself, and whether space, time, and distance are truly fundamental, or only temporary patterns resting on something deeper still? Part 12. Is reality fundamentally information? Some physicists suspect space is not fundamental, that information is. That distance, position, and geometry emerge from deeper rules, like patterns forming from invisible code beneath the surface of existence. At first, this idea feels almost unsettling. We are used to thinking of space as the stage on which everything happens, a vast, silent container holding stars, planets, and people. We imagine information as something that moves through space, signals traveling across distances, data stored in physical places. But this emerging perspective gently turns that intuition inside out. What if space itself is not the container, but the result? To approach this idea, it helps to think slowly, to step back from equations and imagine how reality might be built at its deepest level. Physics has taught us that many things we once thought fundamental are not. Temperature, for example, feels basic and real, yet it emerges from the motion of countless particles. Pressure, solidity, even color, all are collective effects, not primary ingredients. Perhaps space is similar. In this view, the universe at its foundation is not made of locations and distances, but of relationships, interactions, yes-no answers, correlations, bits of information that describe how one thing relates to another without requiring a background grid in which those things sit. Distance then becomes a derived concept, a way of summarizing how strongly or weakly different pieces of information are connected. This sounds abstract, but hints of it appear throughout modern physics. In quantum mechanics, particles do not have definite positions until they are measured. Instead, they exist in states of possibility, described by information rather than location. What matters is not where a particle is, but how its properties relate to other systems. Even more strikingly, entangled particles can share information instantly, regardless of the distance between them. From the perspective of space-time, they may be far apart, but informationally, they behave as if they are a single system. This suggests that space is not the deepest layer governing connection. Connection comes first. Space may come later. There is also the curious behavior of black holes. When matter falls into a black hole, it seems to disappear behind the horizon, but physics insists that information cannot be destroyed. The details of what fell in must, somehow, still exist. Many theories suggest that this information is encoded not in the volume of the black hole, but on its surface, spread across the horizon like a delicate two-dimensional script. This idea leads to something profound, that the amount of information in a region of space depends not on its volume, but on its boundary. As if the universe is, at its core, more like a projection than a solid object, a three-dimensional experience emerging from deeper informational rules. If this is true, then space is not something that exists independently. It is a convenient language we use to describe how information is organized and exchanged. Think of a digital image. On the screen you see landscapes, faces, depth, and distance. But beneath that visual richness lies something simpler, a grid of pixels, each holding a small amount of information. The image feels continuous, yet it is built from discrete units. Zoom in far enough, and the illusion of smoothness fades. Now imagine reality working in a similar way, not with pixels in space, but with bits of information giving rise to the experience of space. In such a universe, asking what exists between 2 points may be the wrong question. There may be no in-between at the deepest level, only a rule describing how strongly two elements influence each other. What we perceive as distance would simply be how long it takes for information to flow, How many steps are required for a change in one place to affect another? This perspective offers a gentle explanation for why space seems to break down at the Planck scale. If space is emergent, then zooming in does not reveal smaller pieces of space. It reveals the limits of the approximation, the point where the language of geometry stops being useful and the language of information takes over. It also reframes the idea of motion. Objects do not move through space so much as they update their relationships. A particle changing position is really a shift in which other systems it is most strongly connected to. Motion becomes informational change, not traversal of a pre-existing grid. Time, too, may emerge this way. Instead of flowing independently, it could arise from the ordering of informational updates. One state follows another, not because time pushes it forward, but because the rules governing information allow only certain sequences. Cause and effect become patterns in data, not events laid out on a universal clock. From this vantage point, the universe feels less like a machine and more like a computation, not in the sense of something artificial or mechanical, but in the sense of a system evolving according to precise abstract rules. This does not make reality cold or empty. Quite the opposite. It suggests that meaning is woven into the structure of existence, that what matters most is not where things are, but how they relate, how they influence, how they encode and share information. As you lie here now, quietly listening, notice how your own experience mirrors this idea. Your awareness is not spread evenly through space. It is a pattern of connections between sensations, memories, thoughts. The feeling of being here emerges from information flowing within your mind, not from any single location. Perhaps the universe works the same way. If reality is fundamentally informational, then space is not the foundation of existence, it is the interface, the user-friendly display that allows complex relationships to be experienced as places, paths, and distances, a translation layer between deep rules and lived experience. This could explain why the universe is so consistent yet so limited, why it allows structure but enforces boundaries, why there is a smallest length, a fastest speed, a maximum density of information. These are not arbitrary constraints, they are the limits of the interface. Beyond them, the underlying system still exists, but not in a form we can visualize. Physics, in this sense, becomes an act of decoding, not uncovering smaller objects in space, but uncovering deeper rules beneath space. Rules that generate geometry the way grammar generates language. And like any language, space works beautifully within its domain. It allows stars to form, planets to orbit, life to arise. It gives us a stable, navigable world. But it is not the ultimate truth. It is the story reality tells itself when information organizes in a particular way. There is something deeply peaceful in this thought. It suggests that when we reach the limits of space, when distance dissolves and geometry fails, reality does not end. It simply changes vocabulary. What lies beneath is not chaos, but structure of a different kind. Quiet, abstract, consistent, a foundation that does not need size or shape to exist. And as this idea settles gently, another question waits just beyond it. If space and time are emergent from information, what happens when information itself reaches its limits and the universe begins to guard what can be known at all? Part 13. Why nothing can be perfectly still. At the smallest scales, stillness disappears, particles jitter, fields fluctuate, even empty space vibrates with energy. Motion may be unavoidable, and space itself may be defined by that restless activity. At first, this idea feels counterintuitive. Stillness seems natural. When you lie quietly, when the room is silent, when nothing appears to move, it feels as though motion has paused. But physics tells a very different story. What feels calm to your senses is not the absence of motion, but motion so perfectly balanced that it leaves no trace on your awareness. Even now, as you rest, nothing about your body is truly still. Atoms vibrate with thermal energy. Molecules shift and collide. Electrons do not sit in fixed orbits, but exist as clouds of probability, always in motion, always changing. Stillness, it turns out, is not a physical state, it is a perceptual one. As we descend towards smaller scales, this becomes unavoidable. In classical physics, it was once possible to imagine a perfectly motionless object. If you removed all forces, slowed something down completely, and waited, it could rest forever. This idea fit comfortably within Newton's laws, where motion only changed when acted upon. But the quantum world refuses this simplicity. According to quantum mechanics, particles cannot have both a perfectly defined position and a perfectly defined momentum. This is not a limitation of instruments, it is a property of reality itself. The more precisely you try to pin something down, the more violently its motion becomes uncertain. This is known as the uncertainty principle, but that name can be misleading. It is not about ignorance, it is about inevitability. If a particle were perfectly still, its momentum would be exactly zero. To know that, with certainty, its position would have to become completely undefined, spread across all of space. Conversely, if you try to localize a particle precisely, its momentum must fluctuate. Motion emerges not as a disturbance, but as a requirement. This means that absolute rest is forbidden at the most fundamental level. Even in a perfect vacuum, where no particles exist, motion does not vanish. Quantum fields still fluctuate. Energy briefly appears and disappears. These fluctuations are not errors or noise. They are the lowest energy state the universe allows. Physicists call this the zero-point energy, the residual motion that remains even when all classical motion has been removed. It is the hum beneath silence, the quiet trembling of existence itself. This trembling is not optional. If all motion were somehow removed, the equations of quantum mechanics would collapse, fields would become undefined, space would lose its structure. Motion, in this sense, is not something that happens in space. It may be what gives space its meaning in the first place. As you approach the smallest scales, this restless activity becomes more intense, not less. At the Planck scale, space-time itself fluctuates violently. Geometry stretches and collapses, directions blur. The distinction between here and there begins to fade. In such a regime, stillness is not just impossible, it is incoherent. Time, too, is affected. Motion is how time reveals itself. Without change, there is no before or after. If everything were frozen, time would not pass, not slowly, but not at all. And yet, the quantum world refuses to freeze. Change persists, even in the lowest energy states. This suggests something profound. Time may not be a backdrop against which motion occurs. Time may be a measure of motion itself. Remove motion, and time dissolves with it. This idea has unsettling consequences. If nothing can ever be perfectly still, then the universe is never at rest, not even at its beginning, not even in its emptiest regions. There is always activity, always fluctuation, always a subtle reshaping of reality. This is why the idea of a static vacuum is misleading. Empty space is not empty. It is alive with invisible motion. Fields rise and fall. Virtual particles flicker into existence. Energy pulses quietly through the void. These fluctuations are small, but their effects are real. They can be measured. They influence forces. They contribute to the behavior of matter and light. In some cases, they even shape the expansion of the universe itself. What's remarkable is how gentle this activity is at large scales. The violence of quantum motion averages out. Fluctuations cancel. Space appears smooth. Time flows steadily. Stillness emerges as an illusion created by balance. But as you move inward, that balance breaks. Motion becomes uneven. Fluctuations dominate. Nothing holds still long enough to be defined in classical terms. Objects become processes, locations become probabilities, identity becomes relational rather than fixed. This is why attempts to describe the deepest layers of reality often abandon the language of objects entirely. Physicists speak instead of interactions, fields, networks, and relationships. Reality is not made of things that move. It may be made of motion itself. There is something quietly comforting in this realization. Stillness, as we experience it, is not threatened by this restless foundation. it is supported by it. The calm you feel now arises because countless motions beneath you are in equilibrium. The universe is not quiet because nothing is happening. It is quiet because everything is happening together. Your breath is steady because molecules move predictably. Your body is warm because atoms vibrate. The ground beneath you feels solid because forces fluctuate in stable patterns. Rest emerges not from stillness, but from rhythm. This also reframes the idea of permanence. If nothing can be perfectly still, then nothing is truly frozen in time. Everything is in the process of becoming something else. Change is not an interruption of existence, it is its default state. Stars burn because particles move. Galaxies evolve because matter flows. Even the constants of nature may reflect deep symmetries of motion rather than static laws carved into reality. At the smallest scales, existence is less like a collection of objects and more like a quiet storm, endlessly active yet governed by precise rules that keep it from unraveling. This is why the universe does not collapse into chaos despite its constant motion. The fluctuations are constrained, balanced, limited by principles that prevent infinite instability. Motion is allowed, but not without structure. And so, nothing can be perfectly still, not because the universe is careless, but because it is carefully constructed to avoid stillness altogether. As you drift deeper into rest, it may help to let go of the idea that calm requires immobility. The universe itself is proof that motion and peace are not opposites, they are partners. The quiet you feel now is not the absence of movement, it is the harmony of countless motions woven together so smoothly that they feel like rest. And as we continue this gentle descent toward the foundations of reality, one last question begins to form. If motion is unavoidable and stillness impossible, what does that say about the ultimate nature of existence itself? Part 14. What happens if space truly stops existing? If space vanishes at the smallest scale, then where no longer applies. Objects cannot be located, events cannot be placed, reality becomes relational rather than spatial, defined only by interactions, not positions. This idea is difficult to hold in the mind because almost everything about human experience depends on space. You are somewhere. Your body has boundaries. Sounds come from directions. Even your thoughts feel like they happen within you. Space is the silent stage upon which all experience unfolds. So imagining its absence feels like imagining silence without time or color without light. Yet at the deepest levels of physics, this possibility is taken seriously. Not as speculation for its own sake, but as a consequence of following the equations to their natural end. If space-time becomes unstable at the Planck scale, if distance loses meaning, then space may not be a fundamental ingredient of reality at all. Instead, it may be something that emerges. To understand this, it helps to think gently, not visually. When we say space stops existing, we do not mean that everything disappears into nothingness. We mean that the concept of location no longer applies. There is no grid, no background, no empty container in which things reside. There are only relationships. In such a reality, asking where something is would be like asking where a melody is located. A melody does not exist at a point in space. It exists as a pattern, a sequence of notes related to one another in time. Remove the relationships, and the melody vanishes. But while they exist, the melody is real, even without a physical location. Some physicists believe space-time works the same way. At large scales, relationships between events organize themselves into something that looks like space, distances, directions, geometry. But at the smallest scales, those relationships may exist without any spatial structure at all. Space would then be a secondary effect, not the foundation. This idea quietly overturns centuries of intuition. In classical physics, space is the stage and matter is the actor. In modern theories that push beyond the Planck scale, the stage itself may be built from the interactions between actors. There is no theater without the play. If this is true, then the smallest scale of reality is not made of points in space, but of connections, exchanges of information, interactions, correlations. Events are not located next to one another, they are linked. And from those links, space emerges the way temperature emerges from moving molecules. No single molecule has a temperature. Temperature is a collective property. In the same way, no single interaction may have a position. Position may arise only when enough interactions align into a coherent structure. This perspective reframes some of the deepest mysteries in physics. For example, quantum entanglement, the strange phenomenon where particles remain connected no matter how far apart they are, becomes less mysterious if distance itself is not fundamental. If space is emergent, then far apart may be a property that appears only at large scales, not something that limits deeper connections. In a spaceless reality, entanglement is not spooky, it is natural. The same idea appears in certain approaches to quantum gravity, where spacetime is described as a network, not a network laid out in space, but a network from which space arises. The nodes do not sit at coordinates. The connections between them define what distance eventually means. In such a framework, asking what happens inside the smallest scale is the wrong question. There is no inside, no outside, only interaction. This has profound implications for causality as well. We are used to cause preceding effect, one event leading to another along a timeline laid out in space. But if space and time both fracture at the smallest scales, then causality itself may soften. Events may not happen after one another, but with one another, as correlations within a larger pattern. Cause and effect blur not into chaos, but into structure without sequence. This does not mean the universe becomes random. It means order exists without the familiar scaffolding of space and time, a different kind of order, one that cannot be drawn on a map. As you rest now, letting these ideas settle slowly, notice how quiet this conclusion is. Space does not end with a crash. It does not tear or collapse in a dramatic way. It simply fades as a useful concept. Below a certain scale, the universe stops answering spatial questions, and perhaps that is a kind of kindness. If space truly stopped existing at the smallest scales, then the universe protects itself from infinite division. There is no endless tearing apart into smaller and smaller places. Instead, reality becomes whole again, not in size, but in description. Everything reconnects. From this perspective, the solidity of the world you experience is not an illusion, but a triumph. Space emerges reliably at the scales where life exists. It gives you direction, distance, shelter. It allows you to rest in a body that has shape and location. The universe offers space where space is useful, and withholds it where it is not. This also changes how we think about beginnings. If space is emergent, then the question, what happened before the universe, may be meaningless. Before requires time. Where requires space. Without spacetime, there is no before and no where, only a transition from one regime of description to another. The universe does not begin in space. Space begins with the universe, and at the smallest scales, that beginning may still be ongoing, not as an event in the past, but as a constant process. Space continually emerges from deeper rules, moment by moment, everywhere. This idea can feel unsettling, but it can also feel grounding. It suggests that the universe is not built on emptiness, but on connection. That reality is not made of isolated points, but of relationships that hold together even when space falls away. Nothing is ever truly alone in such a universe. If space truly stops existing at the smallest scale, then separation itself is an emergent illusion. At the deepest level, everything is linked, not metaphorically, but structurally. And perhaps that is why, even in a vast cosmos, patterns repeat, why laws are consistent, why the same mathematics describes galaxies and particles alike. They are expressions of the same underlying network, seen at different scales. As we move forward in this quiet journey, one final question begins to form. If space can vanish, fracture, and re-emerge, then what does it mean to say that anything exists at all, and where does that leave us? Here, resting comfortably within a universe that feels solid, calm, and real. That is where we drift next. Part 15. Standing at physics' quiet edge. We are living at a moment where human knowledge presses gently against a boundary, not with explosions or noise, but with silence. A place where questions remain unanswered and the universe simply stops explaining itself. This edge is not a cliff you can fall from. It is more like a shoreline at night, where the land fades into water so smoothly that you cannot tell where one ends and the other begins. You walk forward, expecting solid ground, and instead, your certainty dissolves beneath your feet. Physics, for all its precision, has arrived at such a shoreline. For centuries, progress followed a reassuring pattern. Each mystery yielded to better tools, deeper equations, clearer insight. When the atom was discovered, it was not the end. It was a doorway. When the nucleus was revealed, it opened into quarks. When space and time were unified, it revealed gravity's deeper nature. Each answer invited another question, and the universe seemed endlessly willing to respond. But now, the questions are different. At the Planck scale, the universe no longer answers in familiar language. It does not say yes or no. It does not offer a smaller structure or a deeper layer. Instead, it grows quiet. Our equations still exist, but they no longer agree. Our concepts still have names, but they no longer apply cleanly. Space, time, distance, and causality, the pillars of understanding, begin to soften. This is not failure. It is arrival. Standing at this edge, physicists have discovered something humbling. Understanding may not mean seeing everything clearly. It may mean knowing where clarity ends. There is a maturity in science that mirrors a maturity in life. The recognition that some boundaries are not meant to be forced, only approached with care. What makes this moment extraordinary is how universal it is. No matter which path physics takes, quantum gravity, black hole thermodynamics, information theory, cosmology, the roads converge here. They all arrive at the same quiet conclusion. The universe allows description only up to a point. Beyond that, it does not resist with violence, it resists with ambiguity. As you rest now, breathing slowly, consider how rare that is. Most limits in nature announce themselves loudly. A sound grows too loud to bear. A force becomes too strong to withstand. But this limit whispers. It fades. It invites stillness rather than reaction. Even the metaphors change here. We stop speaking of particles and fields and begin speaking of relationships, networks, horizons. We replace things with processes. Reality feels less like a machine and more like a conversation, one that pauses when we ask the wrong kind of question. And perhaps that is the deepest lesson of this edge. The universe may not be something we fully uncover by taking it apart. It may be something we gradually learn how to ask about. The quiet edge of physics suggests that the form of the question matters just as much as the tools we use to answer it. Throughout this journey, we have followed a single thread inward, from everyday distances to atoms, from atoms to energy, from energy to space-time itself. Each step felt like a descent. But now, standing here, it feels more like an arrival at a high place, a vantage point where the view opens even as the path forward fades. From here, we can see how everything connects. Space limits time, energy curves geometry, observation alters reality, information shapes structure, motion defines existence, and nothing stands alone. Each concept only makes sense in relation to the others. This interdependence becomes undeniable at the edge. It is here that many physicists quietly admit something once considered unscientific: awe. Not the dramatic awe of explosions or cosmic collisions, but a gentler kind. The awe of realizing that the universe is not obligated to be fully understood, that its deepest truths may not fit inside human intuition or even human mathematics, at least not yet. And yet, this does not diminish science. It elevates it. To stand at the boundary of understanding is to participate in something rare. It is to acknowledge that knowledge has texture, that reality is not flat and infinite, but layered and intentional. That silence can be as meaningful as explanation. There is also comfort here. If the universe has limits, then it is not endlessly fragile. It is not vulnerable to infinite probing or collapse into paradox. It protects its coherence by setting boundaries, by refusing to answer certain questions in certain ways, by maintaining mystery at its core. That mystery is not a flaw, it is a feature. As you lie here now, perhaps with your eyes closed, notice how your own awareness works in a similar way. You do not experience every detail of your body at once. You do not feel every cell or track every neuron. Consciousness, too, has boundaries, and within those boundaries, calm is possible. The quiet edge of physics mirrors the quiet edge of thought. You do not need to resolve every question to rest. You do not need complete understanding to feel safe. The universe does not collapse because it contains mystery. It endures because it does. And so, standing here at physics' quiet edge, there is no rush to step beyond. There is no urgency to force the next answer. There is only the recognition that this boundary marks a transition from knowing to wondering, from analysis to reflection. Future generations may step further. New ideas may emerge. New mathematics may find ways to speak where current language falls silent. But even then, there will likely be another edge beyond that one. Another place where explanation softens into stillness. This is not a pessimistic thought. It is a deeply human one. It reminds us that curiosity does not end with answers. It deepens. It becomes more careful, more patient, more aware of its own limits. So as this long journey settles, remember this: the moment space itself may stop existing is not a moment of collapse. It is a moment of transition, from a universe we map to a universe we listen to, from certainty to quiet respect. And here, at this gentle boundary, nothing demands action. Nothing needs fixing. The universe continues to exist beautifully, whether or not it explains itself to us. You are allowed to rest here. The questions can remain open. The silence is not empty. It is simply where the universe pauses and lets you breathe. We have traveled a long way together, not across galaxies or through time, but inward, toward the quiet edge where space, time, and meaning themselves begin to soften. We followed distance until it could no longer be divided. We watched energy bend space and observation fold back on itself. We stood near scales where space-time flickers, where geometry dissolves into possibility, where our greatest theories fall silent, not in failure, but in honesty. What we found there was not chaos, it was not destruction, it was restraint. The universe does not reveal everything at once. It offers understanding in layers, each one stable. Enough to live in, gentle enough to hold together. And when we reach the boundary of those layers, it does not shout an answer. It simply becomes quiet. There is something deeply comforting in that silence. It reminds us that mystery is not a flaw in reality. It is a feature. You exist in a universe that allows stars to burn steadily, planets to orbit predictably, and minds to wander calmly through questions like these. All of that depends on limits, on space-time behaving smoothly where it needs to, and refusing to be pulled apart where it must not. Even now, as you rest, the smallest scales of reality are humming beneath everything you know. Quantum fields fluctuate, space holds its shape. Time flows just gently enough to carry breath after breath. You do not need to understand the Planck length to be supported by it. You do not need to solve quantum gravity to be held by gravity. The universe works quietly, whether or not we can name all its reasons. And perhaps that is the final comfort of this journey. At the edge where space may stop existing, where distance loses meaning and time frays into probability, reality does not collapse into nothing. It simply changes its language, one we have not yet learned to speak. Until then, we live here in the calm middle ground, where floors feel solid, where clocks still tick, where night arrives slowly and sleep feels safe. If this quiet exploration brought you even a moment of peace, curiosity, or rest, I'm deeply grateful you shared it with me. Thank you for being here, for listening, for letting your thoughts drift gently through the deepest questions we can ask. Now, there is nothing more you need to do. No mystery to solve, no edge to press against. Just let the universe keep its secrets for the night, and let yourself rest, knowing that even at physics' breaking point, everything is still quietly, beautifully held.